So the dot product. Again, the beauty of working with vectors is it doesn't matter, 2 dimensions, 3 dimensions, all the rules and everything are going to be the same. Some of the ideas we've looked at. If I've got 2 vectors, neither of which is the 0 vector, then I know that u dot v will be magnitude of u times magnitude of v, cosine of the angle between the 2 vectors. And theta may end up being acute, it may end up being obtuse, depending on what we're looking for. This one's kind of trivial. If either one does turn out to be the 0 vector, well then the dot product would be 0. Algebraically, if I was just to do it, it's still the same idea from 2 dimensions, but again we push it through. In 2 dimensions we got the x value and we multiplied it with the x value and then added the y value multiplied with the y value. So it seems logical when we push it through to the 3rd dimension, now we'll do the same with the z values as well. So that will be u dot v. The properties, again, properties aren't going to change. We know the dot product will go in between these 2 values. So remember, it's multiplied by cos theta. Cos theta goes in between -1 and 1. So therefore the dot product must lie in that range somewhere. U dot v is the same as v dot u. The order doesn't matter. This one was useful. U dot u was equal to x1 squared plus y1 squared. Of course, now in 3 dimensions, maybe I should have added that in there, plus z1 squared, because it's the magnitude squared. That's not going to change. We can think of it like algebra. Whilst we're not actually multiplying, that's what we've got to be careful with. When we expand this out, it's the dot product. So it's a dot u plus a dot v, but essentially the same as algebra expanding out. Over here in algebra we'd look at that and say, how a difference of 2 squares, it does turn out to be the difference of 2 squares. Remember, what we're essentially saying is it's u dot u minus v dot v, and as each of those are the magnitude squared, that's what we end up with, the magnitude of u squared minus the magnitude of v squared. If I multiply by a constant, I could do the dot product first, then multiply by the constant, or multiply one of the vectors by the constant, then do the dot product. It will give us the same answer. This one became very useful for a lot of problems. We know the dot product, if it's equal to 0, then the 2 vectors are perpendicular to each other. And if they're parallel to each other, then the dot product would be out at those endpoints. Well, parallel, collinear is probably better, isn't it? Because we're saying the angle between the 2 vectors, they must meet, of course. Careful how you read this, because clearly the magnitude can't be negative. But what I'm getting at here is, in number 8, if the dot product ended up being positive uv, whatever we get there, then we know those vectors are running in the same direction. Whereas if we did it, the dot product, and we ended up with negative, so it's out at the other extreme, well, those vectors must have been running in opposite directions. Let's look at some problems. Well, first of all, we're going to actually prove that rule with the dot product. So a dot b plus c. Pull them into components. I'm saying, well, a will be a1 in the I direction, a2 in the j direction, and so on. Adding the 2 vectors, b plus c, well, I'd just be adding the components, so b1 plus c1i, and so on and so on. Now let's find that dot product. So a1 will be times b1 plus c1, and so on. Expand the whole thing out, but now if I regroup it a different way, we've ended up with a dot b plus a dot c. So, okay, proven that result for 3 dimensions. Prove these are perpendicular. This one's a little bit quicker. Okay, find the dot product. Oh look, it turns out to be 0. Same as was happening in 2 dimensions. Therefore those vectors are perpendicular to each other. Let's have a look at this. So we have A, we're creating a position vector there, OA. Now, they've given us a hint by playing with the angles it makes with the different axes. We're going to prove this result. Cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. It actually is a very familiar result to us in 2 dimensions. We'll look in 2 dimensions what happens. If it was just in 2 dimensions, there's my vector out there, the angle that's making with each of the axes. So if that one's alpha, that one there would be beta. Well, cos squared alpha plus cos squared beta, well hang on, beta would be 90 minus alpha. Well, that's sine squared. Cos squared plus sine squared is equal to 1. So it actually is this very familiar result, but in 3 dimensions. Let's prove it. Cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. This vector u, now if I was to multiply it just by the unit vector in the I direction, then I must just get A. Dot product, well, the J and the K, they're going to end up being 0. I've just got A. But I also know this. I could do the dot product and get this result. Magnitude of U, magnitude of I, times the cosine of alpha. Well, the magnitude of U will be the square root of each of these components, A squared plus B squared plus C squared, times the cosine of alpha. Therefore, I can rearrange all this and get that cos squared alpha is A squared on A squared plus B squared plus C squared. But I could have done the same if I played with beta, so I would have ended up with that, but now it's the y component, or the j component if you like, that I'm dealing with, because we're going the angle to the y-axis. Or I could have played with the angle to the z-axis and I would have come up with that one. Cos squared alpha equals c squared on a squared plus b squared. If I add all 3 of those together, I get 1. There's our results. I said yesterday that a lot of these vector questions, you could have just as easily put them into the 3-unit paper because of the dimensionless. This one, however, probably not, because it is definitely a 3-dimensional problem, the way it's been written. We have a triangular pyramid. L is the midpoint of AB, M of AC, and so on. Okay, and it looks like they've told us B is AB, so it's sort of like they've made A the origin. And we say, okay, there are all the position vectors coming out from there. Show that LP is a half of negative B plus C plus D. I have to get from L to P. How can I get there? Well, there's lots of different paths I could take. I've chosen to go this way. I'm going to go from L to A, so that will be with a negative of the vector AL. Then I'm going to go from A to D, and then D to P. Now, we know AL is half of AB. L was the midpoint. AD's, all right, we've got that one, that's just D. DP would be half of DC. Minus a half of B plus D. Well, to work out DC, I'm going to have to go head minus tail. So that would be D minus C, and we get our result. But the best bit came next. That is what we had to prove. They've helped us out a bit by saying, oh, look, you could have done a similar thing for the vector MQ and NR, and you would have ended up with these. So you don't have to go and sort those out. At least they've worked that one out for us. I'm going to start with the right-hand side. Seeing we just worked out what LP was, it kind of makes sense. I'll play with that one that we just worked out. So the magnitude of LP squared would be the dot product. So LP dot LP, which we just worked out. So it'll be a quarter of that. Now, if I expand that all out, what do we get? Well, I've got all these B dot B's, C dot C's, and D dot D's. That's going to get magnitude of B squared, magnitude C squared, magnitude D squared in there. Now, I've also got this other expression, 2 lots of that. Okay. What about each of these other ones? I don't have to do the whole calculation again, because if you look at them, there's a pattern emerging. See, LP, if you look in the parentheses, only one of the numbers is negative, and it's B. If you look at our answer, in those dot products in the parentheses, only the ones that are attached with B are the negatives. Okay. So looking at that pattern, I can go, well, MQ squared then must come up with this one. The ones with negatives will be the ones that involve C. And then I could come up with that pattern for NR squared. And so for NR, it was D that was negative. So the ones that will be negative in the parentheses there will be the ones that involve D. I want 4 times that. So 4 times the addition of those 3, I'll end up with that expression there. Not quite what we want. Alright, let's now have a look at the left-hand side. The left-hand side was all of these ones added together. AB was just B, AC was just C, and AD was just D. That's fine. CB, head minus tail. BD, head minus tail. CD, head minus tail. I'll leave the first 3 as they are, because essentially I want to show it's the same as my top line there. But why would I take that out of that form when I'm going to have to get it back in that form? But let's look at these dot products. The magnitude squared would be C minus B dot C minus B, and so on and so on. Let's now expand out each of those. So in the first one I'm going to get the magnitude of C squared minus twice the product, so 2B dot C magnitude of B squared, and so on and so on. For each of those, if I collect everything together there, we do get the same as what I got on the other side. Well, therefore, those two things must be equal. I've ended up with the same thing. So yes, they are equal. So 5C, our dot product.